So I'm going to talk about solving the rocket equation with Kerbal Space Program. Christopher Scott Vaughen, Bluebell, Pennsylvania, and so maybe the first thing I'll do is just introduce this game that is a computer game that maybe you haven't heard of. I just recently learned, well, 2 years ago I discovered this game, and it's really amazing tool for modeling, really. And so I already put into the chat something I'm going to refer to later. There's a link there to a website where I wrote a workbook that includes questions all the way from algebra up to differential equations, some, pre-calc, calc 1, 2, and 3 material, differential equations material. And part of what is particularly important to me right now is that I actually applied for a grant from NASA to teach a introductory rocket science, an introductory math class using rocket science to motivate the math and interest in STEM, and I'm using Kerbal Space Program as a way to illustrate these ideas. So I'm going to get to the differential equations example, and I have 2 examples written out with solutions on that website that I linked there, that sites.google.com. And that video is about my course that I just did in the fall. Anyway, Kerbal Space Program is, it is a model solar system. It illustrates the universality of math and physics. It's really STEM and all in one place, and it really produces a textbook model. It is closer to the textbook than real life, if you think about what that really means, which is really useful for a teacher. It really follows the rules that you teach in, physics and in math, as far as, conic trajectories, and, 2 bodies for the gravity at a time. You have multiple planets and moons that some have atmosphere, some don't. So you have all kinds of fascinating things that I would like to get to. For example, air resistance and trajectories through, I'm going to do that with the rocket equation, but other additional, like projectiles and things. So latest version is 1.11. There are expansion packs. There is a huge community of players. There is a educational version of the game. So there's my, it's a workbook that I'm writing. I have answers there. I have 2 example differential equations problems that I think you could take right into a homework assignment, particularly for like an online scenario now, if you want to give some students a more involved kind of assignment that it doesn't require the game, although the game is a beautiful way of illustrating these ideas. So I have a bunch of videos there, and I have some Desmos and GeoGebra interactives. I have Excel files. I have 1 Mathematica file on there right now for that differential equations example that I will illustrate in a minute. But I just thought it would be worth sort of some context here. This game is really a graphing calculator for me, and I mean that because you can do the math first, and then you can check in the model that this game provides. It is illustrating general principles the way you would say, well, this is what all quadratics look like when you graph them. And then you can change parameters. So you can, just like you would shift the quadratic in the view screen on your calculator, you can adjust thrust and mass and, many parameters and look at the results. So, and it's really an online lab as well, because you're building models, you can do experiments, you can download data into Excel and analyze it. And that's what I did. This is a list of tons of topics, and this is why I wanted to share that website, if any of these things might be interesting. I have most of the work here in chapters 1 and 2, where I have actually taught this class as a kind of intermediate algebra, introduction to STEM, motivates physics literacy, space science literacy, mathematical, principles, and then I've got material that I teach Calc 2, Calc 3 regularly, and I use some of these things are just fascinating, beautiful examples for Calc 2 that I just absolutely love. And but I have basically one example so far. Other ideas for the future, but This is the one thing I have really developed so far with Kerbal Space Program in differential equations. And I have these two videos that are on that website that illustrate it. This is when I first found the game and I hadn't really figured out how to use it yet. It's a pretty long video where I really derive the rocket equation. It's kind of an old video where sound quality is not that good. It's really long and maybe boring for most people. But it's really thorough and it's still there until I make a better one. This is a very relatively short and it is one of the two examples that is in the workbook. So I will go through the other example with you here, and now you'll have two examples to look at if you're really fascinated with this. Okay. So I'll begin with the ideal rocket equation, which was pretty new for me. A couple of years ago, I didn't even know there was such a thing as a rocket equation, but how cool is that? There is a rocket equation. Yeah, and it tells you a change in velocity based on some parameters: specific impulse, gravity, surface gravity, initial and final mass. And this is a screenshot, and it's a picture from the game where I have a rocket on the launch pad, and we can see initial mass and final mass. These are things that you can find in the game. They're data that you can download in Excel, and actually you can even see, dynamically changing as you're playing. You can see the initial height up there. That's one of the parameters I'll need. Specific impulse. I mean, I would love to get into this whole story about the rocket science, but I think I'm going to try to keep moving here. We're going to take a constant thrust. But if you have any questions, it would be wonderful to hear what the questions are, and I would love that helps a little bit, reassure me that I'm making sense. So please interrupt if you have something you want to ask. We have a constant thrust, and this scenario, I'm assuming a solid fuel rocket, so that it's nearly provides constant thrust, at least. Yeah, even in the game, it's not exact, not constant, but in my model in the differential equation, I'll assume a constant there. I've got the engine burn time, and then I've got this drag coefficient, and I wonder if you might have some questions about that. So I will get to that. But first, you see, I have done this ideal rocket equation. The ideal rocket equation tells you how much velocity you would expect based on that parameter of the specific impulse, a measure of the efficiency of the rocket. Basically, how quickly it can eject mass to provide thrust. And this is the surface gravity that is just a parameter here that's basically, well, it's another sidetrack. I'll try to, it's part of the theoretical conclusion as to the speed that we could predict if we didn't have any air resistance and we didn't actually have gravity. I know that you might be wondering, well, I see the gravity number right there, but this is a kind of conversion factor really for, so this is a number that represents the change in the speed without gravity and without air resistance. And it's estimating 544 based on the given numbers we have right there, right? But in this launch, we will have gravity from the planet, and we will have atmospheric drag. So we expect it to be less than the 544. And so I begin now analyzing a differential equation that includes terms for gravity and air resistance. So I will start with total force is change in momentum over time. And that's a product rule, right? And my total is going to have a changing mass. I'll have a changing velocity. I'll have, I'll have the rate of change of the mass, I should say, and that is a variable mass. This key, right? The mass is going to drop because it's burning fuel. So the mass decreases. It has obviously changing velocity. That's the variable v, and this is the change in velocity over time. Of course, the acceleration. This is a term to represent the constant thrust. This is the weight, and this is a term for air resistance with a coefficient for drag, and it's quadratic in the velocity. So it's a nonlinear first order differential equation in v. Right? Now, I will take an assumption that the mass drops from some initial value m0 to some final value mf at some mass burn rate given by lambda. So this will be a function for my mass over time. And you can see I'm going to replace that, right? Okay with that so far? And now this is a chance to teach Euler's method. Maybe you're all familiar with Euler's method, and so I'm in Euler's method. I'm basically solving for the dv dt here, isolating the derivative. So it's really just some basic algebra. I just move this guy over there and divide by that term, and this now is the acceleration at any time t with a constant thrust, initial mass burn rate, some coefficient. We're solving for v, and we have some other constants in this acceleration, right? So that is my differential equation where I'm setting it up for Euler's method, and this is kind of the key principle for Euler's method is to find the velocity at some time n+1 based on its current velocity and whatever the rate of change of the velocity is, and multiplied by some increment of time. So I'm going to replace that guy, right, with all of this. Yep. So here again, I think I have done nothing to change that, right? That's the same. I'm just going to now say, all right, we've got our basic equation in the style that we need for Euler's method, and then we can plug in some numbers to see what happens in an iterative process. By the way, of course, isn't it really neat, an opportunity to talk about, there's the scene in the movie Hidden Figures where there's a really dramatic scene where Katherine Johnson says, use Euler's method, and a student could say, yeah, I know Euler's method, right? And so that's what we're actually working on right here. I don't think they really used Euler's method in that actual calculation, but anyway, here we can learn this sort of fundamental numerical method for solving a differential equation. You've seen that I have plugged in all my numbers, including this guy. This is the burn rate. How did I get that? Burn rate is right there. That is initial. What did I have there? Yeah, initial and final. So it's the rate at which it's burning, right? It's positive. So that's fine. That's what I want. Initial, final, positive burn rate, and I've included it there, and then I can go to Excel because maybe this is a tedious process to do by hand when you have perhaps you want to break up an interval, like in this particular example, right? I had 10 seconds. And so what I did was I took increments of half a second. That was my delta t. Right? So when I plug in my velocity at, initial velocity and my delta t, and I use these other constants in our equation, and then I can get the velocity at time 0.5, and then I can use that time 0.5 and the new velocity to get the next velocity, and this is an Excel spreadsheet result that shows the velocity over time. I have that Excel spreadsheet there where you can actually adjust the numbers, right? So I think that's a nice thing to experiment with. Change these parameters, initial final mass, drag coefficient, burn rate, so the thing is that if we are actually if we have the game available, then you could build your own rocket in the game, and you'll have a different mass potentially, right, and different thrust, and so this is the opportunity to experiment. And when I do this, I don't, when I'm teaching the differential equations class, the students don't all have, I'm not expecting them to have the game. So what I can do is I can hold the video of the launch with the values that I used in the question, and then I can show the video and say, did you get that answer, right? Or I can have them. I guess I love that idea that maybe I'll post the video on the course management Blackboard and say check your work with the game. That's really fun to have that. I think I enjoy that. I think that they enjoy that, checking their work with the game, right? So that was Excel, and then I have learned enough Mathematica to put that process into Mathematica, and I have this file, which maybe what I can do is maybe there's a way I can attach this with the PowerPoint. But anyway, you also have it here in the PowerPoint, right? I have a surface gravity 9.8.
Christopher, you got
yes.
You got 3 more minutes.
Oh yeah. Oh, good. Thank you. So, well, the thing is that I solved it with Mathematica, and I got a very similar picture in terms of the speeds. Let me go to this point where I can look at the result that I just generated with Excel, the result that I just generated with Mathematica, although you can see I'm missing a data point there because I couldn't get it to evaluate. I need some help on the Mathematica to get to evaluate at exactly that instant. But those are the data values that came from the game. I plotted the velocity. You can see this is the velocity, and I think I might have been using the velocity that I actually got from the data from the game. There's a curve of best fit for the velocity, and with that curve of best fit, of course, I can integrate that on the calculator over the period of that engine burn. The integral 2134.69. So I'll add the initial height. That's my estimate. That's really close to what happened, and that was just really fun. It was a real model in the computer that we could interact with. We could change. It's entertaining and engaging, and it was satisfying to see. So I am at the end here, and I'm thrilled if you have any questions.
Okay, let's thank Christopher for a wonderful talk first, and then any questions for Christopher? Okay, I have a quick question.
Yes.
So you were using the software, the program, Kerbal program.
Yeah.
How difficult is that for the students, like in a Calculus 1 class? Is that easier to implement that, or?
Well, so I am not using it in a traditional math class. I think first of all, I think maybe some of you are looking at what does this mean to me? It might be something that a club could find as a really engaging, a math club, physics club, rocket club, right? And you can work with integrating with other topics of math besides differential equations, but definitely this is a perfectly well-suited topic for those students. So it's a bit much to really fit into a traditional class as something that they would, as students, during the class. But I think that on this workbook here, I have questions like even this, I don't require them to have the game, right? To engage with the idea of the rocket equation. And then I could just show them a video from the game. And I think it's fun, engaging for me as the instructor, either in the classroom, in a computer lab, or even on Zoom, to turn on the game and say, what do you think? Should I put, another booster on, and then we'll put in some numbers for the, so that's something I could do. And I think it's more than most instructors would want to do, but I think you will find in this workbook some questions where, you don't have to have the game. So, what I'm also doing is I'm experimenting with this kind of like a sort of math and physics literacy course that is where we got a grant, where we bought the game, and we're working with this. I'm working with the students to get them to
Just
use
one
it.
more.
Yeah,
I saw the link with the workbook, right?
yeah,
But could you send that to Brian so that Brian can put that on the web page? So
sure,
that, yeah, because it's in the chat right now.
yeah,
We may lose it in the chat, so that's the reason.
sure. Yeah.
Thank you so much for the talk. Any other questions for Christopher?
Yeah, this is Brian Winkle. I look forward to posting that, but it sounds like you have this marvelous tool to engage students, and they can dig deep to see what the mathematics is, even if they don't understand it on the surface. They can say, oh, it's nothing
Yes.
more than
Yes.
Distance equals rate times time, where rate changes,
in so many places. And for example, we can just, in the intermediate algebra class, I have a graph of velocity over time, and we looked at the average velocity. I introduce, the notion of the tangent there with that intermediate, and the acceleration. So absolutely, that's right. Yeah.
I stepped in, but can videos of rocket flight be impressive when students see it now because of this, do you think? I mean,
Oh yeah. I mean, one of the things that I did in the Calc 1 chapter for this workbook is I watched a YouTube video of a SpaceX. I think it was one of their Starlink, and I just hit pause on the video every second or every 10 seconds or something, and I just hit pause in the video and wrote down the speed.
okay.
And then it is the project in that assignment, in that that has nothing to do with Kerbal in that particular case, and they're just and the questions are to get a model for the velocity, and then take a derivative and find the acceleration at any point, and
Okay.
then I think we can calculate the g-force that the rocket is experiencing from that. So
Cool.
yeah, and if you just YouTube search on Kerbal Space Program, and you will see people are building the Starship. They've built Falcon 9s that carry the Tesla Roadster. The Starship that's right now being tested in Texas. There are very accurate models of that. I think like we could model that mathematically also, and so it's very creative environment, a playground where you really can download real useful data that is textbook model, accurate. So it's a really neat opportunity. Yep.